In this video, we will finish our discussion of nuclear chemistry by going over fission, fusion, and nuclear synthesis. For fission, this refers to a process where we take a heavy nucleus and break it up into smaller parts. So this equation represents one example where we're taking a uranium-235 nucleus, bombarding it with a high-energy neutron. This makes an intermediate uranium-236. This is a very unstable species that will rapidly undergo decay and become a barium-141, krypton-92, and 3 more neutrons. So, as we've seen in the previous lecture, that for some of these reactions, we get a final mass, which is less than the initial mass. This change in mass leads to a release in energy. And in this case, the energy can be transferred to the velocity of these particles. If these neutrons released are going with enough energy, they can collide with another uranium-235, make another one of these unstable intermediates, and induce another reaction. So this can cause a chain reaction where one of these high-energy neutrons can initiate another reaction, and so on and so forth, while constantly releasing energy. So this means that these reactions overall can become self-sustaining. There are a few different cases we have for this. So if we have critical mass, that means we have just enough of this uranium-235 that this reaction will sustain at its current pace. So this means that one of these neutrons has to be able to find and react with another uranium-235 nucleus, while 2 more from that reactions are allowed to just escape. If we have a subcritical reaction, we don't have enough uranium-235 in one space that every neutron goes on to react with another uranium-235. So for example, if we have one of these reacting, maybe we have 2 neutrons coming in, so 2 uranium-235s, they're going to make products including 3 neutrons. And if only one of these has enough speed to cause another reaction, we can see that it took 2 to go in and we only got 1 reaction out. So eventually this will peter out. This is not critical. So we call these subcritical mass. Supercritical is when we have so much uranium-235 that the reaction will go out of control. So more than one of these neutrons can go on to react with another one. So we have 1 reaction occurring, we get 3 of these neutrons, and more than one of them can react with another uranium nucleus, and so we propagate and get more and more of these reactions occurring. Okay, so let's look at an energy calculation for one of these types of nuclear fission. We'll look at this reaction again, and let's calculate the energy released if 1 gram of this uranium-235 is reacted according to that equation that we've looked at. In order to do this, like the previous problems, we need to know the mass of all the species involved, and here we're just talking about the nuclei. So we have uranium, the barium, and the krypton nucleus, and then we also need the mass of these neutrons here. So here's the mass of a free neutron. You'll notice first that the units are different here. So this is just in grams of 1 neutron instead of grams per mole like everything else. So let's first find the mass of a neutron in grams per mole. So we'll take the 1.675 times 10 to the negative 24th grams, and that's per particle, and we'll multiply it by Avogadro's number to get the grams per mole. Okay, so now that we have that, we can calculate the change in mass for this reaction. So this is going to be our products minus our reactants. For our products, we have the barium, and we have the krypton, and we have 3 of these neutrons, and then we want to subtract the mass of the reactants. So this is just uranium and 1 of these neutrons. So if we plug all of this in, we get that we're going to lose 0.1873 grams per mole of this reaction, or per molar of the reaction. Okay, so we now have the change in mass for the reaction as written. We can use this to find the energy. So this is this equation, E equals mc squared. We will plug in our mass, 0.1873. Remember, we have to do this one in kilograms. And then the speed of light squared, 3 times 10 to the 8th. And if we plug all of this in, we get to delta E per reaction. This will be 1.686, and that would be joules per reaction. And finally, we want to find out how much energy is released if we just use 1 gram of the uranium. So we will convert that 1 gram to moles using the molar mass of the uranium nucleus, and multiply this by our energy for the reaction. And this gives us about 7.17 times 10 to the 10th joules released from 1 gram of uranium. This is quite a bit of energy. Something else we might consider too for this reaction is if this uranium nucleus necessarily has to split into barium and krypton. And no, it doesn't. There are plenty of other reactions that are possible as long as the mass number and the number of protons is balanced across all of these. These are viable reactions. They may not be the most abundant, but these can all happen as a possible fission reaction. And as long as the final mass is less than the initial mass, these will all release some energy. These are utilized in nuclear power plants, often from a setup similar to this, where at the core you have a reaction where you're bombarding the uranium with neutrons. This can release energy and other high-powered neutrons to set off this chain reaction. This energy is going to be heating up the surrounding fluid, and this can be transferred to a boiler where it'll boil hot water. This will turn into steam, and the high-pressure steam can power a turbine to generate energy. The recondensed water can be put back into the boiler, and after the coolant transfers energy to the steam bath, it can also be recycled into the core. Another important feature here are these control rods. These are going to be made out of elements that can accept a few extra neutrons without undergoing their own fission reaction. These are very important to keep the amount of neutrons in this reaction controlled so that we stay at critical mass and don't go supercritical. We can also look at another type of nuclear reaction. So we have this nuclear fission, which we know is exothermic. Here's a reaction for a nuclear fusion, where we're adding together 2 hydrogen nuclei. And hydrogen 1, if that's a nucleus, that means it's just 1 proton. So these are basically just 2 protons coming together to make a deuterium nucleus. So this is going to be 1 neutron plus 1 proton, and releasing a positron. What do you think the sign of delta E for this reaction would be? And it turns out that this reaction is also exothermic. Let's take a look at the calculation of this. So in this case, we're going to do per mole of protons instead of per mass. And here's our following reaction. There's something a little tricky in this setup. It is giving us the mass of the atoms, which is not just the nucleus. It means the electrons are included. However, this reaction, the way it's written, is a reaction of just nuclei. So we have to consider this when we are writing out the equations for these problems. So to set this up, we still need the change in mass. And this will be our products minus the reactants. And so for our products here, we have our deuterium nucleus. So this is the 2.01410. And since it's just the nucleus, we have to subtract this mass of an electron. But we're also producing 1 positron, which as an anti-electron would have the same mass. So we'll add in the mass of an electron. And then we minus the reactants. And so in this case, we have 2 of these protons, which are going to be a hydrogen minus its electron. So when we plug this all in, we can see that these electron masses will cancel out in the product side, but in the reactant side, we'll end up with 2 times the mass of an electron here. If we plug all of this in, we get about 4.420 times 10 to the negative fourth grams per mole for this reaction. So if we plug this in to our delta E, and this is our delta E equals mc squared, we get 4.42 times 10 to the negative fourth. Remember to convert to kilograms, and our speed of light squared. And this gets us 3.98 times 10 to the 10th joules. Now this is per reaction, so this is for the reaction. We have to be careful, this question said per mole of protons. So this reaction uses 2 protons, so if we wanted per one individual proton, we'd divide this by 2 to get about 1.99 joules per mole of protons released in this reaction. One thing that you'll also see here is the sign here, so these should be negatives. Drop the negative. If you get a change in mass here that is negative, you know this is going to be energy released. This is just talking about delta E straight up. So since energy is released, this should have a negative sign in front of it, indicating that this is also an exothermic reaction. Okay, so we saw that both fission and fusion can be exothermic. Now this won't always be the case. There's certain regions where this is true, and it's going to depend on the element. So you'll recall this table where we looked at the binding energy per nucleon, and we can compare it to the mass number. So you'll see that if we have things with a relatively low mass number, often if we make them into something that has a higher overall mass number, we'll actually end up with a higher binding energy per nucleon. So this difference here, right, is energy that can be released as an exothermic reaction. Similarly, if we have something that's really heavy with a high mass number, and we split it up into smaller components, there's also a difference in binding energy that goes up. So energy will be released in this case as well. If we look, this will be true on the two sides all the way until we get to the highest peak on this graph, which is occupied by iron 56. So if we have things with a lower mass than iron 56, for the most part, if we smash them together and make something with a higher mass number, we will get something with a higher binding energy per nucleon, and that'll be exothermic. So we have fusion is going to be exothermic for nuclei lighter than iron 56, and likewise for things that are heavier, when we split them apart, we'll gain some of this binding energy. And so this is true that fission will be exothermic for nuclei that are heavier than iron 56. The last thing we're going to talk about is nucleosynthesis. So for the first part of this, we will talk about natural nucleosynthesis, and this is how pretty much all the elements that we observe in the universe were made. So after the initial Big Bang, which was extremely high energy and had enough energy to essentially bring nuclei, protons, close enough together with neutrons that we could actually make the first hydrogen nuclei. So that took a lot of energy to overcome the electrostatic repulsion, but then thanks to the strong force, once we made those were able to hold together. So after the initial Big Bang, where we had these really light elements, we were able to make all the rest of them through other stellar events in places like stars. So in a star, if you got enough of these nuclei together, you can build up enough energy with enough speed that you can start these fusion reactants. In our sun, for example, the core temperature is approximately 1.5 times 10 to the 7th Kelvin. This is hot enough and high enough energy to slam together hydrogen nuclei and cause these fusion reactions, which can release energy and cause more fusion reactions. So the sun is basically a giant fusion reactor where we can take light elements and smash them together to build heavier elements. You'll note, though, and going back to that diagram, that fusion is only exothermic for elements lighter than iron. So if we only had things like solar power to build the elements, any element higher than iron, we would not find in the universe. So fusion is only going to release energy. We can only make things like the sun from fusion reactions with elements lighter than iron 50. So where do the rest of the elements come from? Well, these come from very rare, super high energy interstellar processes. So there's a few examples of these, but one example would be something like a supernova. So this is when a very large star explodes. These have very high energies. So temperatures end up being about 1 times 10 to the 11th Kelvin or even hotter. So this is high enough energy that you can get even heavier particles colliding and making these heavy elements. Note that overall, this still has to have a negative delta G to be spontaneous, but the direct formation of an individual nucleus would actually be endothermic in this case. The extra energy has to come from the explosion of the star in order to make these elements that we otherwise couldn't make by combining nuclei. We can also do nucleosynthesis in the lab to get novel elements. This is often done using particle accelerators. There's a few different types, but the premise is generally the same. So we take an ion in a magnetic field and accelerate it very, very fast. The advantage of the magnetic field is this is something you do in a vacuum and apply a field, and as you're accelerating this particle using normal electrostatic interactions by changing the polarity in the field. So you can get this particle flying extremely fast with very little resistance. And since it's just constant acceleration, eventually it'll have enough speed and enough energy that if you slam it into a target, you can induce a nuclear reaction. These are very controlled and obviously at levels such that this won't be even anywhere near critical. These are subcritical. You usually just get a few reactions and then it's done. So 1 per particle that you've accelerated in the accelerator. There's a few examples of these. So we can get something like this reaction with molybdenum and a proton to make technetium. This is an interesting element actually. It's a little bit lighter than some of the ones that we've made, but it was theoretical. This isn't something that we normally observed on Earth because the nuclear physics of it are such that it's very improbable to be made naturally, but we were able to make this in this reaction with molybdenum and releasing 2 more neutrons. Another reaction, for example, is a reaction with some uranium-238 and a carbon-12 ion. This element that was produced in this case was californium, and it got its name from being made actually here in California at what is now the Lawrence Berkeley National Labs.